Welcome, everyone, to today's deep dive. We are so glad you're joining us.
Yeah, really excited for this one.
So today we're exploring a fascinating stack of historical and scientific notes, and they all center around an American geochemist. His name is Clair Patterson.
Right. Patterson lived from 1922 to 1995.
Exactly. And our mission today is to, well, really understand the extraordinary life of this guy. I mean, he achieved this monumental scientific milestone. He literally discovered the exact age of the Earth.
Which is a massive achievement on its own.
Huge. But the wild part is, he only achieved that to realize his own data was hiding this horrifying global secret. So we're going to uncover how his stubborn refusal to, ignore a tiny anomaly turned him into this accidental crusader.
A crusader who fought a 30-year war against a massive industry.
Yeah. And ultimately altered the very blood flowing in your veins today. Like you listening right now.
It's an incredible story.
So I want to set the scene. It's the early 1950s. Imagine a scientist standing inside a laboratory in Chicago.
But we have to clarify, not a normal lab.
Right, no. Erase the image of like a dusty academic room with a Bunsen burner. We're talking about a room this man has scrubbed 4 times over.
4 times, just obsessive cleaning.
Yeah. He boils his chemical acids twice, just to be absolutely sure. He filters every single cubic inch of air coming into the room, and he distills the water until it is as perfectly clean as mid-20th century science will physically allow.
He's going to extremes.
Extremes. And he's doing all this to measure a whisper of a trace element. He's looking for lead.
Right.
And we're talking about parts per billion here, locked away inside a tiny fragment of an ancient rock.
Just unimaginably small amounts.
Exactly. But every single time he runs his mass spectrometer to, measure these microscopic amounts, the number that comes back is just wildly, impossibly wrong.
There's just way, way too much lead.
Right. And you have to wonder what that feels like.
Oh, the specific psychological toll of this moment for a researcher? It's profound. I mean, we are conditioned by history books to think of scientific discovery as this sudden flash of brilliance.
Right, like the apple falling on Newton's head.
Exactly. The light bulb illuminates. But this
Mm-hmm.
is the complete opposite. This is a creeping, cold dread.
Because he knows he didn't mess up.
Right. He looks at his pristine equipment. He knows his methodology is flawless. And so the realization hits him not as a revelation, but as a horror.
Oh, man.
The contamination isn't a lab error. He didn't, forget to wash a beaker. The lead is in the air outside the window.
Wow.
It's in the rain falling on the roof of the university. It's being carried on the wind across oceans.
It's the cold vertigo of realizing the problem isn't in your instrument, right? The problem is the world itself.
Yeah, exactly.
I was thinking about this, and it's kind of like trying to hear a pin drop in a completely 100% soundproof room.
Okay, I like that analogy.
Like you've insulated the walls, you've sealed the doors, you're literally holding your breath. But you can't hear the pin drop because you suddenly realize the walls themselves are vibrating.
Oh, wow.
From like a heavy metal concert that is somehow playing everywhere on Earth, all at once. The noise isn't inside the room. The noise is the planet.
That captures the scale perfectly. I mean, he built the quietest room on Earth to listen to the oldest rock on Earth, and all he could hear was the deafening roar of a contaminated planet.
And I really want to make this clear to you listening right out of the gate. This story isn't just about rocks.
No, not.
Or, geochemistry or some abstract academic dispute. This is about why you and everyone you know have measurably less poison in your bodies today.
It is a direct physical connection.
Exactly. Between this man's obsessive scrubbing of that 1950s lab and your current neurological health. But to grasp the scale of the poison he found, we really have to understand what Patterson was originally trying to measure in that scrubbed room in the first place.
Right, we have to rewind a bit.
Yeah, to the scientific puzzle that started all of this. What was the goal?
Well, so in the late 1940s and early 1950s, Patterson was working at the University of Chicago. He was alongside geochemist Harrison Brown and an engineer named George Tilton.
Okay.
And they were trying to solve a problem that had defeated generations of scientists across multiple disciplines. They wanted to determine the exact age of the Earth.
Which is wild to think about, because up to that point, humanity had no reliable concept of deep time.
None at all. I mean, in the 19th century, Physicists like Lord Kelvin tried to calculate the Earth's age by measuring how long it would take a molten sphere to cool down.
Right, just basic thermodynamics?
Yeah, and they came up with estimates of maybe 20 to 40 million years.
Which seems old, but it's not even close.
Not even close. Geologists and biologists, they looked at the fossil record and the slow erosion of mountains, and they argued it had to be much, much older. Hundreds of millions of years at least.
Because evolution takes time.
Right. But nobody had a clock.
Until they realized the clock was built into the atoms themselves.
Exactly.
By the mid-20th century, the theoretical method was in place. It's called uranium-lead dating.
Now, the fundamental mechanism here is fascinating to me. We all hear the term radioactive decay, right?
Sure, it's a common term.
But how does it actually function as a geological timepiece?
Well, it relies on the instability of certain heavy elements. Uranium, specifically isotopes like uranium-238 and uranium-235, they are inherently unstable.
Unstable meaning they can't stay in their current form.
Exactly. The nucleus of the atom is packed with so many protons and neutrons that it literally cannot hold itself together permanently.
It's just too heavy.
Right. So over vast, unfathomable periods of time, it decays. It ejects particles from its nucleus alpha and beta particles and transforms into a chain of entirely different elements.
It literally changes its identity.
It does. It becomes thorium, then radium, then radon, tumbling down the periodic table until it finally hits an element that is stable.
And that stable endpoint is lead.
Exactly. It stops at lead.
The crucial part being that this decay doesn't just happen randomly, right?
No, not at all. The rate at which uranium transforms into lead is a fundamental constant of physics. Like, it is completely immune to heat or pressure or chemical reactions. You can't speed it up or slow it down.
Precisely. It operates on a half-life.
Okay, break that down for us.
So if you have a block of uranium-238, it takes about 4.47 billion years for exactly half of it to decay into lead-206.
Just half of it.
Right. So if you have a closed system, say a rock that crystallized and trapped uranium inside it millions of years ago, letting no uranium escape and no new lead enter, you can look at the precise ratio of uranium to lead inside that rock today.
Right. It's often compared to an hourglass. But that metaphor actually falls a bit short, I think, because sand falls at a linear, steady rate.
Yeah, that's true. Radioactive decay is exponential.
It's more like flipping a billion coins at once. You know exactly what percentage will land on heads, even if you don't know which specific coins will do it.
Oh, that's a great way to put it.
If you can count the heads, the lead, and the tails, the remaining uranium, you can calculate exactly how many times the coins have been flipped. You can read the time.
That is a much more accurate visualization of the statistical mechanics involved, yeah. So the physics were understood, but applying this to the Earth, that was the hurdle.
Right, because you can't just pick up a rock from, like, a riverbed in Illinois and date the Earth.
No, because the Earth is this relentless recycling machine.
Like plate tectonics, right?
Exactly. Plate tectonics are constantly subducting crust into the mantle, melting it down and spitting it back out through volcanoes.
The ultimate recycler.
Yeah, and the weather erodes mountains into sand, which compresses back into sedimentary rock. Earth's own rocks have been chemically reset way too many times to give you the true original age of the planet.
So to find the true age, you need a rock that formed at the exact same moment as the Earth, but which was somehow spared from all that violent recycling.
Right. You need a rock from space.
Enter the meteorite.
Yes. This is why Patterson and his colleagues turned to the Canyon Diablo meteorite.
This is the famous impactor that created the Barringer crater in Arizona, right? The really big crater.
That's the one. The Canyon Diablo meteorite is an iron meteorite. It's a surviving remnant from the very dawn of the solar system.
Like leftover building materials.
Exactly. When the primordial disk of dust and gas was coalescing to form the sun and the planets, chunks of material formed that were never incorporated into a larger planetary body.
They just drifted.
They just floated in the deep freeze of space, chemically untouched for billions of years. And inside this particular meteorite were tiny nodules of a mineral called troilite.
Troilite. Okay, and iron sulfide. What makes troilite so special for this experiment?
Well, when troilite crystallizes from a molten state in the early solar system, its chemical structure happily incorporates lead, but it strongly rejects uranium.
Oh, that's incredibly convenient.
It's perfect. This means the lead found inside a troilite nodule is what we call primordial. It is a snapshot of the exact isotopic makeup of lead present at the very moment the solar system was born.
Completely untainted by any subsequent radioactive decay from uranium.
Exactly. By establishing this primordial baseline from the troilite and comparing it to the uranium-lead ratios found in other parts of the meteorite and the Earth's crust, the math would lock in the definitive age of the entire system.
The theory is mathematically gorgeous, like it's just elegant.
It really is.
But obviously there's a massive catch here. The amounts of these elements inside the meteorite aren't like large chunks you can just weigh on a standard scale.
Not even close.
We are dealing with trace elements, vanishingly small quantities.
We are talking about concentrations of a few parts per million and in some cases parts per billion.
Just tiny.
To actually measure these ratios, Patterson used a mass spectrometer.
Okay, let's talk about that machine. How does it work?
So this is an instrument that takes a vaporized sample, ionizes the atoms so they have an electrical charge, and then shoots them through a powerful magnetic field.
This is where the physics gets deeply cool, I think. Because the atoms are moving through a magnetic field, their flight path actually bends, right?
Yes, exactly.
But heavier atoms possess more momentum, so they bend slightly less than lighter atoms.
That's the key. By measuring exactly where the different atoms hit a detector at the end of the flight path, the machine can sort them by their atomic mass.
It literally separates the different isotopes of lead and uranium.
It does. It's an incredibly sensitive instrument. And unfortunately, that sensitivity is exactly what caused Patterson's nightmare.
Right, because of the contamination.
Yes. The amounts of lead he was trying to extract from the meteorite and measure in the spectrometer were so incredibly tiny that the ambient lead in the environment was drowning out the data.
Like the heavy metal concert from earlier.
Precisely. If a single microscopic dust mote floating in the Chicago air landed in his sample, it ruined the reading.
Just one speck of dust.
Just one. If there was a trace of lead in the water he used to wash his glassware, or a microscopic flake of lead paint from the ceiling, the signal from the meteorite was entirely lost in the noise.
So to solve this, Patterson couldn't just rely on, better math or a stronger magnet.
No.
He had to invent an entirely new paradigm of physical science. He had to invent the ultra-clean room.
Which is wild to think about because he's a geochemist, not an architect or an HVAC specialist.
Right. And this is something we take completely for granted today, like in microprocessor manufacturing or virology labs.
Sure.
But in the early 1950s, this level of obsession was just unheard of.
He essentially had to build a fortress against the microscopic world. He instituted positive atmospheric pressure inside the lab.
So what does that mean, practically?
It means whenever a door opened, air pushed out, preventing unfiltered air from drifting in.
Well, that's smart.
Yeah, and he started using Teflon, which was a relatively new material at the time, for his containers.
Why Teflon instead of glass?
Because glass could actually leach microscopic impurities into his acids.
Unbelievable.
Yeah, he built specialized laminar flow hoods. He forced his team into full-body protective suits. And keep in mind, this was not to protect the scientists from the chemicals.
Wait, really?
No, it was to protect the pristine meteorite sample from the scientists. A single skin cell or a stray hair could contaminate the chemical isolation.
It sounds like a brutal, grueling process of elimination.
It was exhausting. Testing the reagents, refining the distillation of the acids, testing the air, constantly fighting the invisible intrusion of environmental lead.
But this obsessive dedication finally paid off.
It did.
In 1953, he took his meticulously prepared, ultra-clean samples of the Canyon Diablo meteorite to the Argonne National Laboratory.
Right, because they had a new, highly advanced mass spectrometer.
Exactly. He ran the samples, he plotted the isotopic ratios on a graph, and the lines converged perfectly.
They finally matched up.
And the calculation yielded an age of 4.5 billion years.
To be exact, his published number was 4.55 billion years, plus or minus 70 million years.
We really need to pause and appreciate the sheer magnitude of this achievement.
It's massive.
The figure Patterson arrived at in 1953, born out of that incredibly stressful, scrubbed-down lab, was so remarkably precise and the methodology so impeccably sound that it remains the undisputed scientific consensus today.
Think about that. Modern science, armed with satellites, supercomputers, and lasers, we've essentially just confirmed Patterson's math.
He found the true age of the Earth.
It was the holy grail of geochemistry, a monumental achievement that guarantees your name in the textbooks forever.
So this is where my mind naturally halts and asks,
Yeah.
why did he keep going?
Right. You'd think he'd be done.
Exactly. He beat the puzzle, he found the number, Any normal person would publish the paper, secure their tenure, go on a lecture tour, and enjoy a quiet, highly respected academic life.
That is exactly what almost any other scientist would have done. But we really have to look at the psychological makeup of Clair Patterson here.
Okay, what do you mean?
Well, the very obsession with purity that allowed him to date the Earth is the exact trait that prevented him from resting. Because even in his pioneering clean room, even after all the boiling and scrubbing and filtering and Teflon, there was still phantom lead showing up in his blanks.
Okay, for those of us not spending our weekends in a chemistry lab, a blank is a control test. Right?
Yes. You run the exact same procedure with the exact same acids and water, but without the meteorite sample.
So in a perfect world, a blank should read 0.
It should be entirely empty.
But Patterson's blanks never read 0.
No, they didn't. He was still getting trace readings of lead. Now, a pragmatic scientist would simply take the reading from the blank, subtract it from the reading of the meteorite sample, call it background noise, and just publish the data.
Right. They would accept that doing science on Earth means dealing with Earth's dirt. Just say, I got my 4.5 billion years. I'm going to ignore this little smudge on the data sheet.
But Patterson couldn't. He absolutely refused to write it off. He had to know the mechanics of the contamination.
He wanted to know where this phantom lead was coming from.
Exactly. How was it penetrating the cleanest room in the world? And this relentless questioning triggers a pivot that changes human history.
Wow.
He shifts his gaze from a rock that is billions of years old to the air he is breathing right now. He starts chasing the anomaly.
He traces the lead out of his lab.
Yes.
He tests his chemical reagents again. He tests the pipes in the building. He tests the local soil. And eventually, he starts testing the broader natural environment.
He zooms out.
He begins comparing the lead levels he is finding in the modern 1950s environment against historical baselines.
Yeah.
He looks at modern seawater versus ancient seawater. He looks at human bone and blood samples.
And the data he begins to compile is terrifying.
What did he find?
Atmospheric lead levels hadn't just spiked recently, they had risen dramatically, exponentially over the course of the 20th century. Patterson realized that what the scientific community considered normal background levels of lead were actually massively elevated.
So everyone was just wrong about what normal was.
Completely wrong. The staggering conclusion he reached was that modern humans were carrying vastly more lead in their bodies than people just a century earlier.
Some estimates show that modern humans were carrying several hundred times more lead in their blood and bones than our pre-industrial ancestors.
Hundreds of times more.
The entire surface environment of the planet, the oceans, the soil, the air, the biosphere, was universally contaminated. We were swimming in a planetary bath of heavy metal.
It's hard to overstate how apocalyptic that sounds. And to understand how an entire planet gets coated in a neurotoxin, we have to look at the chronological timeline.
Right, because this didn't just happen naturally.
No. This sudden, massive spike in environmental lead in the 20th century pointed a direct, undeniable finger at one specific technological development.
The introduction of tetraacyl lead as a gasoline additive in the 1920s. And the history of tetraethyl lead is fascinating and, frankly, infuriating. Let's look at the engineering problem it was designed to solve first. In the early days of automobiles, internal combustion engines had a major issue called engine knock.
Right, engine knock. It's essentially premature detonation.
How does that work in the engine?
Well, in a car engine, a piston compresses a mixture of air and fuel inside a cylinder. A spark plug then ignites that compressed mixture, creating a controlled explosion that pushes the piston down and turns the wheels.
Basic combustion cycle.
Yeah, but as automotive engineers tried to build more powerful, efficient engines in the 1910s and 20s, they had to increase the compression ratio. They had to squeeze the air and fuel tighter before igniting it.
And the problem was the fuel available at the time couldn't handle the pressure, right?
Exactly. The heat of the compression would cause the fuel mixture to spontaneously detonate before the spark plug even fired.
Oh, so the timing was all off.
Completely off. This creates a massive mistimed shock wave inside the cylinder that literally sounds like a metallic knocking.
Hence the name.
Yeah. It destroys engine efficiency and, worse, it can physically tear the engine apart over time.
So General Motors tasks a chemical engineer named Thomas Midgley Jr. with solving this problem.
Right, Midgley.
And Midgley systematically goes through the periodic table, testing thousands of compounds to see if adding them to the gasoline would alter its combustion properties. And he hits the jackpot, chemically speaking. He discovers that adding a compound called tetraethyl led to the fuel, smoothed out the combustion perfectly.
It works like magic.
But how does it actually work at the chemical level?
So when tetraethyl lead is exposed to the extreme heat inside the engine cylinder, it breaks down and releases lead oxide particles.
Okay.
These lead particles act as free radical scavengers. They interrupt the complex chain reactions of combustion, effectively raising the ignition temperature of the fuel mixture.
Ah, so it delays the explosion just long enough for the spark plug to fire exactly when it's supposed to.
Precisely. It eliminated engine knock completely and unlocked the era of high compression, high performance engines.
From an engineering standpoint, it's a brilliant chemical solution.
It really was a breakthrough.
But from a biological standpoint, it is an absolute nightmare. I mean, humanity has known lead is a profound poison since antiquity.
Oh, absolutely. The Romans documented the neurological effects of lead poisoning.
Right. So the engineers at General Motors absolutely knew lead was toxic.
They could not know.
So observe the malicious marketing genius at play here. They knew that putting lead in the name of the new gasoline would terrify the public, so they deliberately disguised it. They called the additive ethyl.
Yes, they marketed it as ethyl gasoline, complete with these cheerful advertising campaigns.
It's so cynical.
It is. They completely obscured the fact that they were aerosolizing a known heavy metal out of millions of tailpipes directly into the streets where people lived and breathed.
And the corporate architecture behind this is staggering. The Ethyl Corporation wasn't some rogue startup.
No, not at all.
It was a joint venture formed by the undisputed titans of 20th century industry, General Motors, Standard Oil of New Jersey, and DuPont.
We really have to examine the corporate knowledge and the willful negligence involved here. Because the dangers of tetraethyl lead specifically were flagged by health officials very early on.
Like right when mass production began in the 1920s.
Yes. This wasn't a hypothetical long-term concern for them. It was immediate and brutal.
The workers in the factories manufacturing this stuff started dying.
It's horrific. During the early manufacture at a plant in New Jersey, the acute toxicity was undeniable right on the factory floor.
Because tetraethyl lead is different from normal lead? Right.
Very different. It's particularly insidious because, unlike inorganic lead, which you have to ingest or inhale as dust, telluride is lipid-soluble.
Meaning it dissolves in fat.
Yes, which means it can absorb directly through human skin.
Let's delve into the actual biology of lead poisoning here, because it's so important to understand exactly what this chemical does to the human body. Why is lead so destructive?
Well, lead is essentially a biological imposter. At the cellular level, the human body mistakes lead for essential minerals, primarily calcium.
And calcium is crucial for practically every function in the body.
Especially in the brain. When a neuron wants to communicate with another neuron, calcium channels open up. This allows calcium ions to rush in and trigger the release of neurotransmitters, which carry the signal across the synapse.
But when lead enters the bloodstream, the body gets confused.
Exactly. The lead mimics calcium and passes right through the blood-brain barrier.
It sneaks right in.
But once inside the brain, lead doesn't behave like calcium. It blocks those synaptic channels. It completely disrupts the release of neurotransmitters like glutamate, which is essential for learning and memory.
So it's actively shutting down the brain's ability to communicate with itself.
Yes. It causes oxidative stress, physically damaging the architecture of the brain. In children whose brains are rapidly developing and absorbing vast amounts of calcium to build neural pathways, lead exposure is catastrophic.
It lowers IQ, causes severe behavioral issues, and permanently alters brain development.
And in acute cases, massive exposure over a short time, the brain simply short circuits.
Which brings us back to the 1920s factory workers. The conditions were so horrific that the workers nicknamed the building the House of Butterflies.
Right, because severe acute lead poisoning causes profound neurological collapse. The workers experienced extreme paranoia, physical tremors, and intense hallucinations.
They often reported the sensation of insects or butterflies brushing against their skin.
It's terrifying. Several workers went violently insane, required straitjackets, and subsequently died agonizing deaths.
It was a huge public relations disaster for the Ethyl Corporation. I mean, the House of Butterflies, workers dying violently on the assembly line. The government actually temporarily halted production in 1925 to investigate.
They did.
So with workers hallucinating and dying, how on earth did this massive industrial coalition manage to keep this poison on the market for another half-century?
Well, they survived it through immense financial power and by pioneering what we now recognize as the classic corporate playbook for manufacturing scientific doubt.
The playbook.
Yes. The industry successfully framed the debate. They poured vast sums of money into funding their own favorable research.
Of course they did.
They employed scientists to declare that while acute, massive exposure in a poorly ventilated factory was indeed dangerous, the low-level, widespread exposure from car exhaust drifting through a city was perfectly safe.
They essentially bought the scientific consensus.
They did. They controlled the flow of research funding for 30 years, ensuring that any study looking into the health effects of leaded gasoline was paid for by the people selling it.
That systemic control of information lasted for decades.
Yeah.
Until Clair Patterson.
Right.
Because Patterson was armed with something no one else had, the ultra-trace clean lab methodology he had invented to date the Earth.
Exactly. The industry scientists were using rudimentary tools that couldn't accurately measure trace environmental lead, allowing them to just dismiss small amounts as insignificant.
But Patterson had the precision to prove exactly how much lead was in the environment, and he was developing the chronological data to prove exactly when it got there.
He was a massive threat.
In 1965, Patterson publishes a landmark paper titled Contaminated and Natural Lead Environments of Man. And he does not mince his words.
No, this wasn't a timid academic suggestion.
He plainly states, with hard data, that industrial lead from gasoline was poisoning humanity. He blew the whistle on the entire planet.
He stated unequivocally that the baseline levels of lead in human bodies that the medical establishment considered normal were, in fact, dangerously elevated due to industrial contamination.
It was a formal, rigorously documented scientific declaration of war against the Ethel Corporation and the broader lead industry.
It absolutely was.
Now, one might naively assume that once a scientist of Patterson's caliber publishes undeniable proof driven by immaculate cleanroom science, the industry would have to capitulate.
You would hope so.
You imagine them issuing a public apology, pulling the product, and changing the gasoline formula immediately.
That is the romantic view of scientific progress.
Right, but the reality is far more brutal.
Much more. They didn't apologize. They didn't alter the formula. They leveraged their massive institutional power to try and destroy his career.
Which brings us to the 30-year siege. We often celebrate the eureka moments in science, but we rarely talk about the grueling endurance required when your discovery threatens one of the most profitable industries on the planet.
It's a heavy burden.
Let's talk about the professional cost of Patterson, because the blacklisting he endured was extensive.
Oh, almost immediately after he started raising the alarm about environmental lead, Patterson found himself frozen out of the very institutions that should have supported him.
Just locked out.
Yes. The lead industry wielded extraordinary influence over research funding and government panels. The historical record indicates that a major, long-standing research contract he held with the U.S. Public Health Service was suddenly refused renewal.
Wow.
And this was widely understood to be due to direct lobbying from the lead industry.
Think about the dark irony of that. You are a scientist desperately trying to protect the public from a ubiquitous neurotoxin, and the very agency tasked with public health pulls your funding because the poisoners complained.
It's maddening. And the exclusion went deeper. Patterson was deliberately left off a crucial National Research Council panel that was specifically formed to review airborne lead contamination.
The man who literally invented the most accurate methodology on Earth to measure airborne lead was excluded from the panel reviewing airborne lead.
Yes, and it was later revealed, unsurprisingly, that this same NRC panel included scientists who had deep, ongoing financial ties to the lead industry.
It was regulatory capture in its purest, most transparent form.
They didn't just disagree with his findings, they actively tried to silence him by severing his financial lifeline and excluding him from the official scientific and regulatory conversation.
We have to look closely at the architect of this denial, the main antagonist of this story, Dr. Robert Kehoe.
Ah, Kehoe, yes. He is a central figure in the history of industrial toxicology.
Who was he exactly?
He was the lead industry's principal medical consultant and their longtime scientific gatekeeper. He founded the Kettering Laboratory of Applied Physiology at the University of Cincinnati.
And who funded that lab?
Almost entirely funded by companies like General Motors, DuPont, and Ethel.
Convenient.
Very. For decades, Kehoe was the undisputed voice of authority on lead exposure in the United States.
So what was Kehoe's fundamental argument? How did a trained physician justify pumping a known neurotoxin into the atmosphere?
Well, Kehoe's methodology was incredibly convenient for his sponsors. He established what became known as the Kehoe paradigm.
What's the paradigm?
His argument rested on the premise that lead is a naturally occurring element in the Earth's crust, and therefore humans have always had some level of lead in their bodies.
Okay, sounds plausible on the surface.
Right. He argued that this natural baseline of lead was harmless and that the slight incremental increase from automobile exhaust posed absolutely no threat to public health.
But wait, how is Kehoe defining this natural baseline? Because the world was already polluted, right?
That is exactly the flaw Patterson identified. Kehoe was measuring the lead levels of, say, Mexicans in rural areas or agricultural workers and comparing them to heavily exposed factory workers.
Huh?
He found lead in the rural workers and declared it natural.
Even though the gas was everywhere by then?
Exactly. He demanded absolute, perfect clinical proof of acute harm, like the immediate hallucinations seen in the factories, before he would admit that low-level environmental exposure was dangerous.
So if you aren't hallucinating butterflies, you're fine.
That was his stance. He assumed that if you couldn't prove it was actively killing someone today, it was safe.
It's a brilliant, cynical defense. It's exactly like a tobacco company paying a doctor to say that everyone coughs. Coughing is natural, and therefore cigarettes are fine, unless you can prove a single cigarette caused a specific tumor.
Yes.
Kehoe was defining natural based on a world that his own employers were already actively contaminating.
And because Kehoe's laboratory controlled almost all the research on the subject, his paradigm became the accepted medical dogma.
But Patterson was a problem for him.
Oh, Patterson was arguably the worst possible opponent for Kehoe, because Patterson's entire career, starting from dating the Earth, was built on achieving absolute, unassailable proof.
He had a sheer, unyielding stubbornness.
Yes. When he lost his funding, when he was ridiculed as a crank by Kehoe's well-funded colleagues, Patterson didn't retreat.
What did he do?
He leaned into his ultra-trace clean lab methodology. He realized he had to bypass Kehoe's rigged arguments about modern human health entirely.
Because arguing with a paid industry doctor about the blood of modern humans is a trap, since Kehoe controls the narrative there.
Exactly.
So Patterson changes the battlefield entirely. He turns away from biology and goes back to geology.
He goes back to what he knows best.
He sets out to find the physical, historical proof of what the world looked like before the 1920s.
He reasoned that if lead levels had truly spiked in the 20th century due to gasoline combustion, there would be a physical, undisturbed record of it trapped somewhere in the Earth's systems.
So where does he look?
He started by analyzing deep ocean sediments.
Okay, let's break down the oceanography here. Why look at mud at the bottom of the ocean?
Well, the ocean is not a perfectly mixed bathtub.
Right.
It has distinct layers based on temperature and salinity, a process driven by thermohaline circulation. The surface waters mix relatively quickly with the atmosphere, but the deep abyssal waters of the ocean are isolated and move incredibly slowly.
Like over centuries.
Yes. Furthermore, particles from the surface slowly sink over thousands of years, forming pelagic clay on the ocean floor. By taking core samples of this deep-sea mud, Patterson could basically look back in time.
It's a geological time machine.
Exactly. Using his clean room techniques and isotope dilution mass spectrometry, Patterson measured the concentration of lead in the surface waters versus the deep ocean.
But how did he know he wasn't just measuring a difference in how fast the mud settled?
Great question. He needed a proxy to ensure he wasn't just measuring a difference in overall sediment rates, so he cleverly compared the lead levels to barium.
Barium. Okay, why barium?
Barium is another heavy metal that enters the ocean through natural geological weathering, but it isn't used heavily in industrial applications.
So the barium acts as a control for natural weathering. If lead and barium move together, it's natural. If lead spikes alone, it's not.
Precisely, and the results were staggering.
What did the mud show?
The ratio of lead to barium in the surface waters was wildly skewed. The surface waters were heavily contaminated with massive amounts of lead, while the deep, ancient waters, which hadn't been exposed to the modern atmosphere, were incredibly clean.
It was a massive piece of evidence. But the ocean is fluid, right? It mixes over centuries. Patterson wanted a more precise timeline.
He wanted a year-by-year record.
He wanted to trace the contamination exactly. So he went from the deep ocean to the deep freeze. He went to Greenland.
Yes, and this is one of the most heroic logistical feats in environmental science. Patterson understood that glaciology held the ultimate key here.
How so?
As snow falls on an ice sheet like Greenland year after year, century after century, the weight of the new snow compresses the older snow underneath it.
Just squishes it down.
Right. It transforms from porous snow into a transitional state called firn, and eventually into solid, impermeable ice.
And crucially, as it turns into solid ice, it traps microscopic bubbles of the atmosphere.
Yes. It creates a literal frozen time capsule of the Earth's air from the exact year that snow fell.
That is amazing.
If Patterson could get samples of that ancient ice and melt it down in his clean room, he could measure exactly how much lead was in the atmosphere centuries ago.
But wait, the physical logistics of doing ultra-clean trace metal chemistry on a glacier have to be mind-boggling.
Oh, it was a nightmare.
You can't just hack a piece of ice off with a pickaxe, right? Because the steel in the pickaxe will instantly contaminate the sample with more lead than you were trying to measure.
Exactly. The precautions they had to take were extreme. They had to drill deep into the ice sheet. But thermal drills and mechanical drills use fluids and metals that are full of contamination.
So how did they do it?
When they finally extracted these long cylinders of ice, the outer layer of the core was heavily contaminated by the drilling process itself. Patterson's team essentially had to build a sub-zero clean room.
A clean room on a glacier.
Pretty much. They used specialized acid-wash tools to carefully shave away the outside layers of the ice core, working inward until they reached the pristine, untouched center.
So they are performing microscopic surgery on a block of ice in freezing conditions just to protect a chemical signal measured in parts per trillion.
Yes, and they analyzed the cores layer by layer, going back hundreds of years. And the graph that Patterson eventually produced from this ice core data is arguably one of the most important scientific documents of the 20th century.
What did the timeline show? I mean, what did the graph look like?
The graph showed that for millennia, atmospheric lead levels were practically flat.
Just a straight horizontal line.
There was a tiny, barely perceptible bump during the Roman Empire when they began smelting lead for pipes and coins, and another small rise during the Industrial Revolution.
Okay, so minor fluctuations.
But then, starting in 1923, the line on the graph suddenly goes vertical.
Wow.
It creates a massive, exponential hockey stick shape that correlates perfectly, exactly, with the introduction and widespread adoption of tetraethyl lead in gasoline.
The ice doesn't lie.
No, it doesn't.
Patterson used the chronological fingerprints of the Earth itself to completely corner the Ethyl Corporation. Kehoe and his corporate backers could argue about human biology all day long. They could demand endless medical studies on whether a specific factory worker's tremor was caused by lead or stress.
Right.
But they could not argue with the frozen atmosphere. They couldn't argue with 4 billion years of geological record-keeping and a pristine timeline trapped in a glacier.
It was an evidentiary checkmate. It simply bypassed the industry's manufactured doubt completely. Patterson proved definitively that the baseline Kehoe called natural was actually a massively elevated state of acute global contamination driven entirely by a single industry.
Truth, armed with enough immaculate data, eventually becomes too heavy for even the richest corporations to suppress.
It just takes a long time.
Which brings us to the culmination of this 30-year war. The data finally reached the desks of the people who could actually write laws.
Yes. The turning of the regulatory tide is always slow, but by the 1970s, it was undeniable. Armed with the mounting mountain of evidence built directly on Patterson's clean room methods and his ice core data, public health advocates finally had the ammunition they needed.
And there was also an unexpected technological catalyst that accelerated the ban, right? The catalytic converter.
Yes, that was a crucial practical factor. In the 1970s, the newly formed U.S. Environmental Protection Agency, under the authority of the Clean Air Act, was mandating reductions in smog and tailpipe emissions.
Because cities were choked with smog.
Exactly. To meet these new standards, auto manufacturers had to install catalytic converters on all new cars.
And what do catalytic converters do?
They filter out harmful pollutants from the exhaust. But the lead in tetraethyl gasoline physically poisoned the precious metals inside the catalytic converters, rendering them completely useless within just a few tanks of gas.
So the EPA had dual motivations: the undeniable Patterson-backed proof of a massive public health crisis and the mechanical necessity of making catalytic converters actually work.
Exactly. So the EPA initiated a phase-down of leaded gasoline. It wasn't an overnight ban, it was a gradual reduction designed to give the petroleum industry time to retool their refineries and, to prevent sudden economic shocks.
Right, you can't just turn off the gas supply overnight.
But the trajectory was firmly set. By the mid-1980s, major reductions in leaded gasoline usage were achieved.
And this culminated in a full, total U.S. ban on leaded gasoline for on-road vehicles in 1996.
A huge milestone.
It's worth noting briefly that the global timeline varies. Some countries banned it earlier, some much later. But the U.S. ban was the monumental domino that really broke the back of the industry's global narrative.
Absolutely. The phase-out of tetraethyl lead in the United States is one of the greatest environmental and public health victories in modern history.
Which brings us to the ultimate question for you, the listener. What does this mean for your life today? What did this 30-year grueling fight actually buy us?
Yeah.
What did Clair Patterson's obsession actually achieve for humanity on a practical level?
Well, it achieved a measurable public health miracle. We have the data from comprehensive public health surveys tracking blood lead levels in the American population during this exact period.
Okay, what did the survey say?
From the late 1970s, as the phase-down began, through the mid-1990s, as the ban took full effect, average U.S. blood lead levels plummeted.
By how much? Let's talk numbers.
Roughly 80% or more.
Wow, an 80% reduction in a systemic neurotoxin across the entire population.
Yes. The drop in human blood lead levels perfectly mirrored the drop in leaded gasoline production.
The correlation is undeniable.
It is practically 1-to-1. As the lead came out of the gas, it came out of the air, and it came out of our bodies.
The profound implications of that are staggering. By forcing that 80% drop, Patterson didn't just win a scientific debate in an academic journal. He physically altered the chemical composition of the human body on a mass scale.
He really did.
He improved the neurological health of entire generations. There's fascinating research, actually the lead crime hypothesis, that suggests the massive drop in violent crime rates in the 1990s correlates directly with this removal of lead from the environment.
Yes, that's a heavily discussed theory.
Because millions of children grew up without a neurotoxin, hindering their impulse control and brain development.
And whether one fully subscribes to every aspect of the crime hypothesis or not, the underlying biological reality is undisputed. Eliminating that constant low-level neurological damage vastly improved the cognitive potential and cardiovascular health of hundreds of millions of people.
Incredible.
It is rare to find a single scientist whose personal stubbornness translates so directly and so measurably into the physical betterment of humanity.
But the bittersweet reality of this story is that Clair Patterson never really got a massive parade down Fifth Avenue.
No, he didn't.
He wasn't on the cover of Time magazine as the man who saved the world's brains. For the vast majority of his career, he was treated as a nuisance by the scientific establishment and actively persecuted by industry.
He did receive some measure of late recognition, though. In 1995, he was awarded the Tyler Prize for Environmental Achievement, which is one of the most prestigious awards in environmental science.
But he died shortly after, in that same year, 1995.
Yeah. The Tyler Prize was a wonderful honor, but when you look objectively at the scale of what he accomplished, defining the age of the planet and simultaneously saving its inhabitants from mass chemical poisoning, it feels like a fraction of the honor he truly deserved.
It really does.
It arrived at the very end of a life spent mostly enduring a siege rather than being celebrated.
It's the strange, brilliant arithmetic of his life. I mean, he is rightfully famous in geology circles for dating the Earth to 4.5 billion years. That single calculation secures his name in history.
Without a doubt.
But his greatest contribution to humanity didn't come from the number he was looking for. It came from the number he wasn't looking for.
The phantom lead.
The annoying, impossible contamination that was ruining his meteorite data. He fought a battle he didn't start, against an industry he had no initial intention of fighting, simply because his scientific integrity would not allow him to ignore the anomaly. He refused to lose to a lie.
It is a profound testament to the power of pure intellectual honesty. He let the data dictate his life's work, regardless of the personal cost.
So as we wrap up this deep dive into the sources, the takeaway is clear. The next time you hear someone cynically say that a single person can't change the world, or that a system is too big and too well-funded to fight, think of Clair Patterson.
Absolutely.
He didn't use a grand speech to change the world. He didn't have a massive PR team or a super PAC. He used cleaner and cleaner measurements. He used boiling acid, distilled water, and an unyielding refusal to compromise his data.
Just relentless science.
Year after year, enduring blacklisting, enduring ridicule from highly paid industry experts, he just kept measuring until the truth was simply too precise to argue with.
The quiet, staggering fact remains. Practically everyone listening to this right now has measurably less poison flowing through their veins today simply because one exhausted geochemist in 1950 Chicago refused to shrug off a strange reading.
Which leaves us with a final, lingering thought to mull over. Patterson's world-saving crusade was entirely born from investigating the noise the annoying, inexplicable contamination that was ruining his actual prestigious experiment.
Right.
It makes you wonder, right now, in laboratories all over the world, in all fields of science, how many incredibly important, world-changing discoveries are being dismissed as mere experimental errors or background noise. If our instinct is to constantly calibrate our instruments to ignore the anomalies we don't expect, how many times are we quietly throwing away the very data that could save us? We want to thank you so much for exploring these sources with us today. Keep questioning the noise.